Next time I'll write a very detailed explanation.
Now that's the question we don't get.
All right, let's open up to page 135. We're going to take a look at another theorem today related to synthetic division. We were dealing with the remainder theorem yesterday, how we noticed that the remainder from synthetic division was the same as the function value from the equation. So it was nice that we had that connection. We're going to take a look at the factor theorem today.
Borrow a calculator.
Back or front, doesn't matter. All right, I think this factor theorem is going to be a little bit, I'm hoping, kind of common sense to us. We are familiar with the division process. We're familiar with a certain terminology related to division. If x equals a is a 0, meaning an x-intercept, what would the related factor look like? For instance, if we had an x-intercept at 2, what would the factor look like from the equation? Go ahead. It would look like x minus 2, okay? So, using that logic, if a is an x-intercept, then the factor would look like x minus a, okay? We kind of saw that connection yesterday when we were looking at the graphs and how we wrote the factors and confirmed with synthetic division that they were actually factors. So that was a little bit of a review. Now, if we were to take this factor of x minus a and do the synthetic division process, what would the remainder be? If you look at the 3 graphs that we did yesterday, okay, we did synthetic division with an x-intercept. What was the remainder? Go ahead, Alicia. 0, okay? If it's a factor, it goes in evenly, meaning there's nothing left over, aka the remainder is 0. Okay, I think we're used to that concept. Factor means nothing left over. Okay, goes in evenly. So we're going to use this factor theorem idea, a remainder of 0, to help us with some questions. Is 2x plus 1 a factor? Okay, meaning does it go in evenly? Is the remainder of 0? We want to show our work and then explain what that means in terms of the graph. So we can approach this 2 different ways. If you want to show that it's a factor, we somehow just need to identify what the remainder is. Is it 0 or is it not? How do you want to go about determining what the remainder is? We could do one of 2 things. It just depends on what you're comfortable with or what you feel like doing, what seems intuitive to you. Quinlini? Okay, so if we find the 0, which would be negative 1/2, we could plug that in for all the x's according to the remainder theorem, and our answer would represent the remainder. Okay, that's one thing we can do. A different thing you could try to accomplish is if you're just trying to figure out the remainder, you could actually go through the synthetic division process and look at that last number. Okay, is it 0 or is it not? So there's more than one way to tackle this. You just got to figure out what the remainder is. Let's see. If we have a calculator, plugging in negative 1/2 might not be too difficult. Okay, but for some of us that don't have a calculator, maybe synthetic division would be the better option. Okay, so you can do either one. I don't have a calculator with me right now, so I'm going to go ahead and do synthetic division. The powers are in order. We're not missing a power, so we'll write down the coefficients as they are. All right, drop the first number times negative 1/2 would be negative 1. Add to 3, we get 2. Multiply negative 1/2 again we'll get negative 1. Add to negative 11, we'll get negative 12. Multiply by negative 1/2, we get 6. Add to negative 6, we get 0. Is 2x plus 1 a factor? Yes, the remainder is 0. Okay. Now, technically, hopefully we realize we're not done with the division process. The coefficient on the x is 2, so you would have to divide the quotient values by 2. That's not necessarily a part of this question or a part of this problem, but that is something that we'll eventually get into doing, so I'm hoping it's starting to become a habit at this point. You got to take a look at that coefficient to see if you have to go a little further. Okay? But nonetheless, for this question, the remainder is 0. So we can say yes, 2x plus 1 is a factor. What is this telling us about the graph of this polynomial? We don't have a graph available to us, but maybe this is kind of hinting at something. What's special about this negative 1/2? What do you think, Noah?
That's where it changes like up or down.
What do you mean by up or down?
Since it's a 0, that's just where it will cross the axis.
That's where it touches the x-axis. Okay, so it might change from above to below or below to above. Maybe that's what you meant by up or down. So x equals negative 1/2 is an x-intercept. Okay, it's on the x-axis. If it's a remainder of 0, it's a function value of 0, meaning a y value. So that's where you are on the graph. In this case, the x-axis. Do you guys think you can do number 2? Very similar question. Okay, is x plus 2 a factor? Show your work, and what does this mean in terms of the graph? Bless you.
Bless you.
All right, now depending if you did synthetic division or if you plugged in negative 2 for all the x's, I'm hoping that we would have gotten a result of negative 34. Does that seem to check out? Okay, so what's that telling us about this x plus 2 divisor? Is it a factor? No, because notice how it does not go in evenly. Okay, we have something left over. So no, x plus 2 is not a factor. Okay. What's that telling us about the graph? What do we know about this x value of negative 2? X equals negative 2. Is it an x-intercept? No. Okay, so x equals negative 2 is not an x-intercept. Okay. So we know the graph is not on the x-axis at negative 2. So that must mean it's somewhere else. Do we know where the graph is located? at -2? Think about the remainder theorem from yesterday. Yeah.
Minus 34.
-34. Okay, this remainder is a function value. It's a location on the graph. So the graph for the first question at -1/2 is located at 0, meaning on the x-axis. For this graph at -2, it's located at -4. So we know we're not on the x-axis, but we actually know where we are located. We can say the point -2, -34 is on the graph. Okay, the remainder is telling you a function value, aka a y value, aka a graphical location. Okay, the remainder is kind of the clue or the key to all this division. Okay, it is something left over, is something not. Looking good?
Yeah.
Sink it in. Okay, we're basically looking for a remainder of 0 if it's a factor, or if it's not 0, we know it's not a factor. All right, let's check out 3. Consider this function, okay, this polynomial. Before we check out the 3 boxes, I want you to think about this. What if I were to ask you to factor that polynomial? What technique would you want to try? Can we roll through our options? There are a lot of them. Is there a GCF? No. Does it fit the I am setup? It kind of looks like it should, but something's actually throwing it off. What's throwing it off? Yeah? It's cubed. Okay, that power of 3. You could do I am if it was a 2, or you could try to do it if it was a 2. Okay, so no GCF, it's not I am. Since it's cubed, we can't do divide and slide. There's not 4 terms, so grouping is out of the picture. It's definitely not a difference of squares, so that's gone. And we're not adding or subtracting perfect cubes that we've recently talked about, so that's gone. So out of all of our options, it looks like none of them work. So we cannot factor this using any techniques that we've discussed. Okay? Say it again.
Complete the cube, is that a thing?
Complete the cube? I don't know if that's a process. I've heard of completing the square.
Yeah,
I know that. But completing the cube, I don't know. Maybe if you want to develop it or create it, go for it.
Okay, I'll
Okay.
become a mathematician and you can teach about me in class.
Sounds good. All right, let's go ahead and try, let's take a look at this though. Okay, so we cannot factor it using the techniques that we've discussed, but maybe we can get around that issue. Okay, we're going to see how synthetic division can kind of help us with that. So take a look at the first box. We're going to divide this polynomial by x minus 3. So our outside number would be positive 3. And then for our coefficients, the powers of the polynomial are in order, but we're missing the power of 2. So we have to make sure we put in that placeholder of 0. Be careful with that. All right, let's drop the 1 and we'll see where synthetic division is going to lead us. Is x minus 3 a factor? Yes, it goes in evenly, okay? So even though we could not factor it from the very beginning, notice how we just found a factor, okay, by doing synthetic division. Now, they do want us to factor the quotient, okay? Maybe we can continue to try to factor a little bit further. So even though the original problem could not be factored, maybe the quotient can be, okay? Maybe we can try some techniques for that. So if we put the x's back into our quotient numbers, we'll get x squared plus 3x minus 4. Can we think of a factoring technique for that? I am. Okay, 2 numbers that multiply to negative 4, add to 3. Negative 4, positive 1. Perfect. No? Flipped. Sorry. Good catch. That's better, right? Okay, so even though we were not able to factor it from the beginning, we just factored it completely. We have the x minus 3 factor that was confirmed by division, but then we were also able to factor the quotient a little bit further, and we got x plus 4 and x minus 1. Okay, interesting. Let's try B. What if we tried to divide by x minus 1? The outside number would be 1. And we'll go ahead and use the same coefficients because it's the same polynomial.
I remember doing this now.
You do? Good.
I think we did. Or we did something similar.
Maybe. Drop the 1 and we'll see where division leads us. So it looks like x minus 1 is a factor, the remainder is 0. And if we take a look at the quotient, putting the x's back in, x squared plus x minus 12, maybe we can factor that. Even though we couldn't factor the original polynomial, maybe we can do its quotient. IM kind of looks like it'd be good for this one, two numbers that multiply to negative 12 but add to 1. X plus 4, x minus 3. Looks good. All right, let's check out the third option. We're going to divide by x plus 4. So our outside number will be negative 4, and we'll keep the same coefficients. Drop the 1 and see where division takes you. We have a remainder of 0, so it looks like x plus 4 is a factor. Let's see if we can take the quotient a little further. Two numbers that multiply to 3 but add to negative 4. X minus 3, x minus 1. Okay. So taking a look at those three boxes there, do you notice a pattern between all three of them? You see it, Travis?
Well, they're all factors, right?
Yep.
And then, when you synthetically divide one of the factors, if you're then able to factor the thing that you give them the quotient, that is, if you give them dividing, you might get the other two factors.
There you go. So notice how, even though we were not able to factor the original, if we can find just one factor, okay, this one, whatever it is, if we can just find one factor, we can use that to help us find the other ones by possibly taking the quotient and factoring that a little further. Okay, so if we can just find one, we can find the rest. And that's pretty powerful with this synthetic division. Okay, we can use that to our advantage. So based off of this, we should be able to write the factors of the original polynomial. Those were the x minus 3, the x plus 4, and the x minus 1. Notice how all of those were the factors in these three examples. So if all of those are the factors, we should be able to find the x-intercepts. Since they all go in evenly, we'll have 3, negative 4, and 1. Okay? So moral of the story, this is pretty powerful stuff. Okay, we could not factor the original polynomial to figure out where the x-intercepts are, so we're using synthetic division to get around that issue. If we can find one x-intercept, okay, one factor, we then can figure out the rest. Okay, we're going to be working on that concept a lot in this unit. Okay, so synthetic division is pretty powerful stuff. We can use it to our advantage. All right, let's go and try some more. If x minus 1 is a factor, what are the other factors? Okay, so they're kind of leading us in a direction here. Instead of leaving it up to us to figure out where a 0 is, we'll eventually get there, okay, because that's a little bit more demanding. They're kind of leading us in a path. So let's go ahead and first test to see if x minus 1 is a factor. Does it go in evenly? we'll do synthetic division to help us see if our remainder is 0. Looking at the polynomial, the powers are in order, no power is missing, so we'll copy down the coefficients. Drop the first number and then divide. Is x minus 1 a factor? Yep, goes in evenly, remainder of 0. So we should be able to take the quotient values, put the x's back in, and factor that further. So taking a look at this quotient, can you think of a technique that would be useful to factor this polynomial, this new polynomial? Yeah?
Use like de-grouping if you want to.
Grouping? Okay, or divide and slide. We went over those two options, whatever you're more comfortable with. So since it does not fit the IAM setup because the A value is 2, so we kind of have no choice in this case to go through the A times C, kind of add to B. So A times C would be -6, B is -1. Can we think of two numbers that multiply to -6 but add to -1? -3, +2. Okay, so it's at this stage that you can either do grouping, okay, replace the middle term with those, or you can do divide and slide. Do we have a preference? Divide and slide? Okay, so we'll have x minus 3, x plus 2. If you prefer grouping, go ahead and do that, whatever you're more comfortable with. So these are the initial factors, but we have to go through the divide and slide process. We'll take the A value of 2 and then divide those special numbers that we found by 2. Notice how 3 over 2 does not simplify, so we'll slide the 2 in front of the x as a coefficient. In the second factor, 2 divided by 2 can simplify to 1. So we should be able to officially rewrite the original polynomial in terms of its factors. So we'll have the original factor, x minus 1, that we proved through synthetic division, but then we have the other two factors that we found from the quotient. So 2x minus 3 and then x plus 1. You ready to try number 6? See how it goes? All right. Very similar question. If x plus 2 is a factor, what are all of the zeros? Okay, a little worded differently here, but the zeros, the x-intercepts we know come from the factors. So essentially, we have to do a similar process by finding all the factors, but we're going to take it a step further by then identifying the zeros. Okay, just one little thing that I know we can do. So let's first see if this divisor is a factor. We'll go ahead and set up our division. Looking at the polynomial, the powers are in order, and we are not missing any. So the coefficients are good to go. Drop the 2, and we'll go through division. Now looking at our division, it seems like our remainder is 0. So we know officially x plus 2 is a factor. Bless you. Let's go ahead and take our quotient values, put the x's back in, and see if we can continue to factor. Okay, find the other factors of this polynomial. Now it looks like our quotient is very similar to the previous one that we did, so it seems like divide and slide or grouping would be another appropriate technique to try here. So a times c would be negative 12, b value negative 1. Two numbers that multiply negative 12 but add to negative 1. Little mind game. Yeah. Negative 4 and 3. All right, so we'll have x minus 4, x plus 3, a value of 2. So we'll have x minus 2, and then 2x plus 3. Okay. So we've officially found all the factors. They want us to now find the x-intercepts, or those zeros. So let's see if we can do that here. Based off the factors that we found, what are the x-intercepts? Can we list them? Go, Julia. 2, okay, from this factor. Negative 3 over 2 from the other factor. There's one more. Yeah? Negative 2. Okay, the original value that we did in synthetic division, the fact that it's a remainder of 0 proves that this is an x-intercept. So try not to forget that first one. We might forget it because it's the very first one that we do, and we're going to get caught up in the math and the factoring, but it's still an x-intercept. So it looks like we have 3. All right. Looks good. All right, let's try 7. For what value of k is x minus 2 a factor of that polynomial? This is kind of similar to what we did yesterday, but now we're dealing with the terminology of a factor. What do you think we can do? There's actually 2 things you can do for this one, and it might not be a bad idea to go over both. You have an idea? Yeah.
You can set the equation equal to 0 and then plug in 2, because x plus 2.
Okay, so we could use that remainder theorem from yesterday that told us the function value is the same as the remainder. So if you were to plug in 2, and for all of these x's, you should get an answer of 0 in this case because you want it to be a factor, aka going in evenly, nothing left over, remainder of 0. So let's solve for k. Oh boy. 2 cubed is 8 times 6, 48. 2 squared is 4 times 19, 76. That seems about right. Exactly, brain math. All right. Negative 76 plus 6 is negative 70, plus 48, negative 22. All right. So solving for k looks like we'll get 11. So this is what we basically did yesterday using the remainder theorem. I'm curious if someone would have approached this using synthetic division. Did you just do it? How'd you set it up?
Oh, you set it up like the normal synthetic division.
Okay.
And just leave k blank for now.
Okay. So doing synthetic division is always going to be an option. The difference with this one is, and it kind of get a little confusing, notice how we have a variable instead of a coefficient. So it might be a little worrisome for some of you because it's not the actual setup that we're used to using. Now, if this is a synthetic division setup, is there something else we can put into this setup that we're trying to verify or prove? 0 must be the remainder, okay, because we want it to be a factor. So we're still trying to figure out what k is, but notice how we can probably figure that out with this setup. If we were to go through division like we normally would, we drop the 6, times 2 would be 12, plus negative 19 would be negative 7, times 2 would be negative 14. And this is when you would add k, but that might look a little weird down here. So notice how you can work through synthetic division to a point, but maybe we can use this 0 to our advantage and work backwards. For instance, if we want a remainder of 0, what must this number be? Negative 6, right? And if this number is negative 6, what does this one have to be? Negative 3. Why? 2 times negative 3 is negative 6, okay? And if this number is negative 3, what would k have to be? 11, because 11 plus negative 14 would give you the negative 3. So there is a way to still complete this problem by using synthetic division. It's more of a thinking process, okay, if you work forwards and backwards, but it's still a technique or a method. Okay, so whichever one you're more comfortable with is completely fine with me. Do you guys think you can choose the method of your choice and try 8? Go ahead and try that one. Either by using the remainder theorem or synthetic division, whatever you prefer. Synthetic division is a little bit trickier because you have to think about it. Yeah. Or more fun, depending on how you want to look at it. Okay. The remainder theorem is a little bit more mathematical, like solving an equation to a point.
Whoa, chill.
People from all races, ethnicities can be nerds.
Blue, chill, dude.
This is negative.
Negative 60? Yeah, right, okay.
That's brain power.
It's fun.
144 divided by 9? 16? Okay.
Yeah, no, I like this more.
Yep, that's good. Okay.
Thanks, my brain.
Negative 16? Good to go? All right, let's check out 9, and then we'll end for today. This one's a little different. We're going to end on a good note. Is x plus 1 a factor? Okay, we can definitely check that. But the next question, how many times is it a factor? So we're going to see how many times we can actually go through division. How many times does it go in evenly? Let's check it one time. Okay, so doing division, is it a factor? Does it go in evenly? All the powers are in order, nothing's missing, so our coefficients are good to go. Drop the first number and then divide.
Oh, wait. Then we do it again. Do it again.
Is it a factor? Yes. Okay, so we know it's a factor at least once. How can we test it to see if it goes in evenly again? Okay, well, I'm going to run out of room, so you can keep going. But what are we going to use as our new coefficients? -3, -4, 1, and 2. We're going to see if it goes in evenly into the quotient this time. Drop the first number and go again. Is it a factor again? Yes. So we're at least twice. Let's see if we can go again.
Oh, I remember stuff like this happening. I remember there was just one problem where we
Yeah.
divide by 15 times.
Wow.
Well, okay, so it was back whenever we first learned how to do this. We were checking to find one of the factors, right? And then whenever we found one of the factors, it didn't synthetically divide, or you couldn't do any factoring things again. So then you had to find another factor again for the quotient of the first factor. So we had to do it a bunch of times. It was a really big equation, so there was like 10 different
Possibilities.
I don't remember how you find them. But
We're gonna get into that.
I know. I remember that it's not too hard, but you get a lot of
Okay, stopped. 3 times.
All right, I got it to be a factor a third time. If we go again,
It don't work.
is it a factor the fourth time? No, because the remainder is 5, right? Okay, so let's see how we could write this polynomial. So f of x, if we were to write out the factors, we know that x plus 1 is a factor, but specifically 3 times. So how can we denote that? Cubed. You'd have x plus 1 times x plus 1 times x plus 1, because you have 3 of them. But then we can just cube it, so we don't have to write it so many times. What is the other factor? When did this stop being a factor? After the third one, right? So then this is your leftover. Not leftover, I shouldn't say that because that's remainder. This is your remaining quotient, right? So negative 3x plus 2. If you take a look at the original equation, you cannot GCF anything. You can't do IAM. You can't do grouping because there's 5 terms. You can't do divide and slide. It's definitely not a difference of squares or an addition or subtraction of cubes. So there's no way for you to factor that polynomial using the techniques we discussed. But synthetic division gives us a way to get around that. So if you can find one factor, notice how you can find the other ones. Okay, it's pretty powerful stuff. We're going to be doing this the rest of the unit.
Could you do like grouping if there's 6 terms?
Grouping of 6 terms. I'd have to look into that. Because you could do 3 and 3, just like 2 and 2, but I'm wondering if it would work out the same way. We'd have to look into that.
You get the idea.
Thank you.
Figure out. Draw a circle. Nobody. Take a chunk out.